Welcome everyone to this section. Today we'll be discussing Module 5 of EC464 Low Power VLSI Design. So in the previous section we dealt with clock logic families. In this section we'll be dealing with the various non-clock logic families, which is fully complementary logic, NMOS logic, pseudo-NMOS logic, past ancestor logic and differential cascade voltage switch logic, DCVS. So non-clock logic is universal in design because of the low power consumption, its reliability, noise immunity, and straightforward delay rule timing. So what is a fully complementary logic? It is same as that of a conventional CMOS logic, where it consists of two transistor networks, pull up network and pull down network. PMOS is used as the pull up network and NMOS is used as the pull down network. Here we can see that this is the connection. The right hand side shows the diagram for how we can connect a PMOS and NMOS to get a CMOS. The inputs given to both the PMOS and NMOS section are same, but only one network will be on at a particular time. And the number of transistors required to implement this gate is 2n, where n is the number of inputs. Suppose we want to make a 4 input gate, 8 transistors will be required because 4 for PMOS network and another 4 for NMOS network, right? And now if you want to make an inverter, this is the circuitry. We provide A as input, A bar is the inverted output. Okay, PMOS and NMOS connected like this. We have the source connected to VDD and the drain is common. Right, here, this is the drain. From where the output is taken, if A is the input, A bar is the output. For a NOT gate, PMOS section is kept at the top, PMOS connected in series and NMOS connected in parallel will result in a NOR gate. In case of NAND gate, PMOS connected in parallel and NMOS connected in series will result in the logic function A dot B the whole bar, which is NAND gate. Right. Now, implementation of various other logic functions can be done in the same context. Next logic family is NMOS and pseudo NMOS. It's a ratio logic. The proper rationing of pull up and pull down network is required for correct operation of the circuit. Here, we do not have any, the pull up network is replaced with a, we do not have a pull up network. We have a pull up network, but it is replaced with a single unconditional load device. The NMOS section or the PDN pull down network is same as it is, and based on the load, based on the load provided, we have two designs for NMOS logic, which is called depletion load NMOS or simply NMOS and pseudo NMOS. So a depletion load NMOS, it consists of the NMOS logic with a load with gate connected to source. Here the fabrication is a bit complicated. So the schematic diagram will be like this. For depletion load NMOS or simply NMOS logic family, we have the pull down network. Pull down network means the NMOS section is same as it is. We're providing the input, it is grounded, and between VDD and the pull down network, we are providing an NMOS whose threshold voltage is less than 0, and we are connecting the gate to VSS, and the output is also taken from the same section. Right. So for an example, a 2-input NAND gate is shown. So the NMOS section when you first draw a CMOS, draw the NAND gate in complementary MOS and take the NMOS section, keep it as it is, and between VDD and the NMOS network, provide another NMOS whose gate is connected to VSS and output section. You can take the output F is equal to A dot B whole bar. So that is how you design a depletion load NMOS or simply NMOS. Now in case of pseudo NMOS, this NMOS transistor is replaced by a PMOS connected to ground. PMOS connected to ground. That means when it is connected to ground, PMOS will be always on. Right, PMOS will be always on. So the number of transistors required in this case will be N plus 1. N plus 1. So this is the same function which we are implementing with the help of pseudo NMOS, means 2 input NAND gate F is equal to A dot B whole bar. So we provide an NMOS circuitry, and between VDD and the pull down network we provide a PMOS which is ground, whose input is grounded. Okay, so that is regarding NMOS and pseudo NMOS. Now moving on to pass transistor logic. Pass transistor or switches that are connected in parallel will give an AND function, or and pass transistor or switches connected in series can provide a OR function. Now we all know that NMOS pass transistor can pass a strong 0 but weak 1. PMOS pass transistor can pass a strong 1 but weak 0. So if you want to implement the logic, we have to allow input to gate. We have to provide input to the gate as well as the drain and source terminals. So this is a simple diagram, switch representation of a pass transistor logic. The same thing when you convert it into an equivalent transistor representation, you get like this. So you have the terminals A and B. A is the input, B is also the input to the transistors M1 and M2. We are providing the signals B and B bar. Okay, and the based on the combination of the signals provided at the gate and either of the two terminals, either the gate or the source, we are getting the required logic function as output. Now suppose in this case that B equal to 0. If B equal to 0, what happens? This M1 transistor will be off, M2 will be on. Since B is 0, so when it is on, what we will get as the output? B itself. So B means 0. So when B equal to 0, in both cases, we are getting the output 0. A dot B means does not have any dependence on A. The output will be 0. Now, suppose B is 1, what happens? This transistor is on and this transistor is off. B is 1, we are getting A as the output. So if B is 1 in the truth table, we get A as the output. A equal to 0, so the output is 0. A equal to 1 and B equal to 1, the output will be A dot B, which will be 1. Right. So these are the next two diagrams shows AND gate in two different representations. Like see here, we are providing A and A bar as the signals to the gate terminals, B and 0 to either of the source or gate, and we get A dot B. Instead, we can also give another way, like A and 0 is given at the source or drain terminals, and B and B bar are given at the gate terminals. Then also we'll get the function A dot B AND gate. Now that is how you design a fast transistor logic. Now another version of fast transistor logic is called complementary fast transistor logic or differential fast transistor logic. It uses a zero threshold transistor and differential input and output signals. So the advantages are the circuit is differential. So the complementary data inputs and outputs are available. Like here we are getting only uh, one output combination. Suppose if it's AND gate, we're able to design only AND gate in case of fast transistor logic. But when we go into CPL, which is an advanced version of PTL, we are able to get both the function as well as its complementary output. But the combination which is given to the input section, the combination which you're providing at the gate and also at the source and drain terminal matters, right? So this is the basic concept. We get the pass transistor logic and inverse pass transistor logic to provide the function and the complement of the function. The inputs given would be same. So we'll see how it is done. So this is a, CPL for or NOR gate. See, you're providing the corresponding inputs and a particular combination at the gate. So here we get the OR gate, F is equal to A plus B, and F bar is equal to A plus B the whole bar. NOR gate also we're able to get. Now that the same applies for AND NAND gate and XNOR and XOR and XNOR gate. Okay, so the output as well as its complement are able to be uh, derived from this, are able to be found from this logic. Now, the next one is differential cascade voltage switch logic. It combines two concepts, differential logic and positive feedback. So, the two complementary logic blocks, the required function and its inverse are simultaneously implemented, and the positive feedback ensures the load is turned off when it is not used. So how is it done? This is the basic concept behind DCVS. We have a pull down network 1 and pull down network 2. The inputs are properly given, and then PMOS section is provided at the PMOS is provided at the top of both pull down network. And in order to provide the feedback, we are taking the input of one pull down network to the out of the next network. So that is the so we are able to get that is a feedback system, and we are able to get two outputs, output and output bar, its complement. So PD1, PDN1 and PDN2 transistors, we are keeping NMOS transistors and they're mutually exclusive. Now advantage is that it eliminates a static power dissipation. The circuit is ratioed, but you can see from the design that the circuit requires more area and the switching power dissipation is also very high. So this is an example for AND NAND gates. See, at this section, you're providing A dot B whole bar. For that, we connect two NMOS transistors in series. Now, when you connect the NMOS transistors in parallel, what you get is, and you're providing the inputs as A bar and B bar. See, here you're providing A and B. So you're getting A dot B whole bar. Here you're providing the inputs to this section A bar and B bar, and you're keeping it in a parallel, you're constructing it as parallel. Okay, so what we get is A bar plus B bar, the whole bar, right? So that will be equal to A dot B the whole bar, and when you take the output bar of it, we will get A dot B, the whole double bar, which is equal to A dot B. That is how you arrive at this output. So A dot B bar, A dot B whole bar and A dot B is the combinations of output and output bar respectively. That is how you design a differential cascade voltage switch logic. And when you provide a clock to this DCVS, we get differential, we get another circuit, differential switch logic, differential current switch logic. Thank you.